All right. Thank you all for joining for this new reading group session organized by ContinualAI. Today we have the pleasure to host Eli Verwimp, who is going to talk about his recent work, Rehearsal Revealed: The Limits and Merits of Rehearsal in Continual Learning. And I think that this is one of the first works trying to summarize and make a bit of order with respect to the rehearsal replay methods that we have out there, and try to pinpoint, let's say, some important aspects that I thought it would be nice for us as a continual learning community to discuss together. And so thank you again, Eli, for accepting my invitation. And thank you all for joining again. I hope this can spark like an interesting discussion about especially replay methods in continual learning. So without further ado, please go ahead, Eli, the stage is yours.
Thanks. Hello, everyone. So as Vincenzo mentioned, I'll present Rehearsal Revealed: The Limits and Merits of Rehearsal in Continual Learning, which is work I've done jointly with Matthias, the Lange Internet Duitelaars, Matthias, who's also here tonight. First, let me introduce myself quickly. So I'm Eli Verwimp. I'm from Belgium. I've done a master in mathematical engineering at the KU Leuven. And I've done my thesis on online continual learning, and which introduced me to the subject and made me interested in starting a PhD at the physics lab of the KU Leuven with Tinne Duitelaars, who is also working on continual learning, among other things. First, before I explain our work, I want to situate our work kind of in the general continual learning scheme. So of the three types of methods, the replay, regularization, and parameter isolation methods, we focused on the replay methods. So these are methods like iCarl, GEM, but most importantly, just experience replay or rehearsal. The motivation for our work comes from different works and different ideas other researchers had about replay and rehearsal and the ways these things acted. And the first quote I want to mention comes from Gradient Episodic Memory, which is a very famous continual learning work. And they stated that obviously minimizing the loss on the current examples together with the memory results in overfitting to the example stored in M being the memory. So they assume that overfitting on a rehearsal memory will happen. And then a second work, 2 years later, I think, is on tiny episodic memories. And they say basically, yes, overfitting happens on these memories, but it doesn't harm generalization because the samples of task 2 are a strong enough regularizer such that the generalization still is okay. And then a third work is GDump. And in GDump, they say that similar or even much worse improvements are noticed in other approaches, suggesting that they might not even be utilizing the memory samples efficiently. So we've got three works, one saying you will definitely overfit, one says you will overfit, but it doesn't harm generalization, and a third work who says we're not even using the memory efficiently enough. So this led us to two questions about rehearsal and the way it worked. The first is, why does rehearsal actually work, even though overfitting on the rehearsal memory occurs? And the second question is, does overfitting on the rehearsal memory influence generalization? And to this end, we formalized two hypotheses. And the first is that rehearsal is effective because the solution you find while training a model with rehearsal ensures that you stay in the same low loss region as the task minimum from which the learning of a new task initiated. The second hypothesis is basically yes to the second question. Overfitting on the rehearsal memory harms generalization capabilities of a model. Before continuing, I want to give an overview of the remainder of the talk. So first I'll give some background into our experiments and how we approached the problem. Then I'll talk about our experiments and how we tried to find answers to the hypothesis. Then I'll talk a bit about the interpretation and then give some relation to other works. And then finally, I'll conclude and we'll have some time for discussion. First background I want to give is rehearsal so that everybody is at least on the same page about what we mean with rehearsal in our work. So in rehearsal, every time a new batch arrives at model to be trained on, we will sample this batch and store a subset of the batch of the samples that arrive at the new model in a memory. And then we use this memory to retrieve old samples and concatenate these old samples to the new batch such that we have a joint batch of new and old samples on which we update a model. And this prevents forgetting as much as possible. Now, these models, these neural networks, we usually, or we always train them by minimizing an objective function, which we call the loss function. And such a loss function you can always write as a sum of other loss functions. For instance, losses on all classes that are available in the data, or all tasks in a continual learning setting, or even all samples that are in your data set. And as long as your data is IID distributed, meaning independent and identically distributed, then each term in this sum will be equally likely to appear in every new batch that arrives at your stream. And if this property is true, then you can prove that stochastic gradient descent will converge to the minimum of the sum rather than one of the terms alone. But in a task incremental stream or any continual learning stream, there's only one term of the sum that's going to be present in the data stream at one. So for instance, if we're training on MNIST and we're training the second task, only the second loss term will be present if there's no measures to prevent catastrophic forgetting, of course. So in this case, stochastic gradient descent will converge to a single element in the sum. To prevent this, we have to, the solution is to approximate previous losses. So if we're learning the second task in MNIST, we have to approximate the first loss. And we can do this, for instance, in rehearsals by storing old samples of previous tasks. Background about that. I want to clarify our hypothesis now, and this figure is mainly sums up the entire paper, and it will come back a few times. So don't worry if there's some parts of the figures yet unclear. The three most important parts of this figure are W1, W2FD, and W2. And these are all models, and they're shown in the parameter space. So we've got a model W1, which has a set of parameters. We've got a model W2, which is, so W1 is a model trained on the first task of any data set, and W2 is a model trained from W2FD, is a model fine-tuned from the initialization of W1 on a second task, and W2 is a model trained with rehearsal on the second task initiated from W1. And our first hypothesis is that rehearsal is effective because this rehearsal solution stays in the same low loss region as the initialization, which we can see here. This is the region with low loss for the first task, and W2 stays within this region. The second hypothesis is that we will overfit on the rehearsal memory, and this harms generalization, which is depicted by the shaded area where the rehearsal memory has low loss, but the test set or the overall data distribution doesn't. So what we actually want to end up is in this region where both T1 and T2 have low loss, but what we hypothesize is that we end in this region where there's some overfitting on the rehearsal memory. Some background on the details of the experiments. We've done all three experiments on that I will show you on MNIST. CipherTen split, mini ImageNet split. Sometimes I will only show the results of mini ImageNet, but if you're interested, the other results are in the paper, or I can show you them at the end of the presentation. All models are trained online without any task boundaries or task identifiers to the model. For MNIST split, we used just a simple MLP with 2 hidden layers. And for the CipherTen and mini ImageNet datasets, we used a slimmed down version of ResNet 18, all with a, shared head. And we optimized models using stochastic gradient descent with a batch size of 10. So let's start with the first experiment, and this is the same figure as we've seen before, but now with real loss values. And these are 3 models trained on mini ImageNet on the first and the second task. So we've got again our first model, which is trained on the first task of mini ImageNet. And we see the losses on the first task as the red line and the losses on a second task as the blue lines. We also see the training trajectory, which is a projection into this 2D plane. These are not actually in the plane, as opposed to W1 and W2, who define the plane in the parameter space. The difference between the left and the right figure is on the losses of the first task, where on the left we have the losses on the test set, on the right we have the losses on the rehearsal memory. Our first hypothesis was that rehearsal is effective because we stay in the same low loss region as the first initial point, the minimum for the first task. We can clearly see this on either left or right figure. So while the loss increases on the first task, we still are in the same region of low loss as the initial point, which is definitely visible on when we look at the losses on the rehearsal memory. Our second hypothesis is that we will overfit on the rehearsal memory, and this does harm generalization, which is also visible from these figures. While the rehearsal memory has very low loss, below 0.5, we see that the loss actually increased on the test set, indicating that our generalization capabilities of the first task are harmed a bit. This is, of course, not a rigorous proof that our hypotheses are true, so we have done more experiments to better validate these claims. To this, we've moved on to experiment 2. And in experiment 2, rather than only have one W1 and one W2, we trained 100 models on the first task and then continued training on those 100 models to 100 models trained on the second task with rehearsal. And in this graph, you can see the loss on the test set of the first task and the loss on the training set of the first task, which align almost perfectly. And regarding the first hypothesis, we can see that this again confirms this hypothesis, that we are still in the same low loss region. Why? If that wouldn't be the case, there would be an increase in the loss and then a decrease again as soon as we arrive in a new low loss region. This isn't the case. We only see a monotonically increasing loss, indicating that we're still in the same low loss region. Similarly, if we go from 1 to the 5th task, we see the same thing happening, except that the losses are now much higher, but we're still in the same region. We only have monotonically increasing loss, indicating again that we did not go to a separate low loss region that has nothing to do with the first found region. Second hypothesis is, of course, that we overfit on this memory, which we can also clearly see. As soon as the loss on the test set starts to increase, the loss on the rehearsal memory decreases and goes to almost 0. A second question we asked with this experiment, like an additional question, now if we, instead of having one W2, what if we trained 2 models from the same initialization? How are those related? And that we can see in these figures. So we calculated the losses on a linear path between W2 and W2 prime, 2 models trained from the same initialization, and they are connected linearly without any increase in loss, meaning there's in the same low loss region as, and the data converge to a point in the same low loss region. Similarly, for if we train for 5 tasks, so W5, W5 prime, there is even a big decrease in the loss on the test set if you look at the linear connection between both. But again, these are both in the same low loss region and not in different regions. A final experiment we've done is, rather than looking at simply the loss values, what we're often mostly interested in machine learning is actually the gradients of the loss, because we use those for optimizing our neural networks, our models. And we've looked at the gradients on both the test set and the rehearsal memory at 3 different points in the parameter space, being again W1, W2, W5, the models after 1 task, 2 tasks, and 5 tasks. And if you look at the gradients for the first task, we see what's expected, gradients with a very small norm, because we're, of course, in the minimum of this task. Now we train for the second task with rehearsal, and we see that the gradients on the test set have already increased at the final training step of the second task, but those on the rehearsal memory did not increase as much. On the 5th task, we again see an increase on the gradient norms of the test set of the first task, but those on the rehearsal memory stayed fairly low. What does this indicate? Again, that we are sort of on the edge of the low loss region and on where the loss is increasing, but we're still on this edge, while the rehearsal memory still thinks that we're in a good area of the low loss region. If we take that back to the figure that we saw in the beginning of the presentation, we can kind of split the training trajectory that's followed in 2 phases. And the first phase is that what happens if you start training on a second task while you've learned the first. In the first phase, the trajectory that's followed when you use rehearsal will roughly align with that of fine-tuning, which is this part in this graph. And then the second phase, you will follow this high loss ridge, as we call it, towards a region where both low loss regions of the first and the second task intersect, and we found a joint optimum. We can see this also in our results. Here you can see the same figure as we've seen before, but on Cypher10 rather than mini ImageNet. And we can see here on the first phase where we more or less move towards the W2 fine-tuned minimum, and then in the second phase follow roughly equal loss contours towards a point where there is a joint minimum. Also take a look at this idea of these 2 phases from the perspective of the losses that we're optimizing. And remember, as I've told in the background, that we can look at these losses as sums of losses. And we can look at the loss in these cases as the loss of the first task and the second task. So in the first phase, since we're in this low loss region that has low loss on the first task, we can say that this loss on the first task is approximately 0, which leaves us with a loss that's almost equal to the loss on the second task, which is exactly the loss that you're optimizing while you fine-tune. So it makes sense that in the first phase, or at least for the first optimized steps, you will do the same thing as you would if you were only using samples from the second task. Now in the second phase, both losses will have converged to more or less the same value, and it will stay this way, because as soon as one loss is higher than the other, the gradient of that loss will influence the other gradient, and they will converge to somewhat similar values and decrease together. Finally, we've done one more experiment me and Matthias, we were reasoning about these how this trajectory worked and how rehearsal worked. And we said, well, if it's true that we're at this point in the loss space of the 2-1 task set, what if we then would be able to just take a few steps back away from this high loss ridge, and then we would, and our hopes were that we would end it in an area like this, at this point, where there's a lower loss on the first task, but the second task still has an equal loss. Now, the problem, of course, is that you don't have access to this loss and the test set loss for the first task, but you only have access on the rehearsal memory losses. But our hopes were that there will be still somewhat of a gradient, some gradients left that will push us away from the ridge. And if you look at the results of these experiments, ER step are the results of these step experiments where we take n steps, update steps only on the rehearsal memory of the first task. Then we can see, especially for MNIST with small rehearsals, with small memory sizes, that there is an increase in overall accuracy of about 10%. And this is by no means like a new method that would improve the state of the art, but more like a validation of our ideas about how rehearsal works. And we can see that also for Cypher10 and Mini-ImageNet, there are increases in the accuracy if we take a few steps back away from this ridge, which we assume to be dangerous for overfitting. For Mini-ImageNet and Cypher10, we used stable SGD instead of normal SGD. So those results validated our ideas that we move towards this high loss ridge, and then we need to take a few steps back because we expect that this high loss ridge is a dangerous place for overfitting on the rehearsal memory. Now, I want to take a few steps outward to different works in and outside continual learning. And the first related work, or the work that I want to point attention to, is Optimal Continual Learning Has Perfect Memory and is NP hard, which is a rather depressing work because they basically say that we have to, after learning a first task, we have to remember all the points that have low loss on this first task. Because if we start learning a second task, we need to find the intersections of the low loss in the first task and the low loss regions of the second task, and then use those intersections to move on to a third task. Then the second work is an empirical work, and they do a similar analysis than we do, but they first train an initial model on a first task, and then from that model they jointly train on a first and a second task, and then they find that this jointly trained model is in the same low loss region as the first model and as a second model that's fine-tuned on the second task. So this means that there is a joint minimum inside the low loss region of the first task, which means that contrary to what the authors of this work said, that there is a good joint minimum inside this low loss region, so there's no need to remember every other possible low loss region. In an ideal situation, probably it's best to know all low loss regions, but this work shows us at least there exists a fairly good joint minimum inside the initial low loss region. Now, a third work is Understanding Deep Learning Requires Rethinking Generalization, which shows that modern neural networks are capable of completely memorizing random data, and that exists a very possible danger of overfitting on data. So this is the good thing that this is why it's a good thing that we stay in this first low loss region, because if we would leave it and then only find a new low loss region based on the rehearsal memory itself, we do not have we do not have any guarantee that this region will generalize as well as the first region does that we found using the entire task data set rather than only the memory. Again, GDump shows that you can actually also fairly efficiently train on the memory alone, but I think this is an interesting work showing the dangers of overfitting on data sets and even random data sets. A bit more into detail relation to another work is with GEM, gradient episodic memories. And gradient episodic memories, the idea is to store samples in memory, and then we calculate a gradient on new samples that arrive at our model. And then we look at what this gradient would do to the loss on the old samples. Does the loss on the old samples decrease? Okay, then we update the model with this new gradient. Does it increase? Then we project the gradient on the new samples such that we have a loss decrease on the old samples as well. And this actually explicitly ensures that we do not leave the initial minimum, such that we're sure that we stay inside this well-defined region. Now with rehearsal, we use the samples in our memory differently. We just concatenate them to the new batch of samples and calculate a gradient based on the old and new samples together. But as we've seen, this has a similar effect that we implicitly ensure that this minimum or this low loss, this is actually, I should have used a different word here. It's not a minimum, it's a low loss region. But this implicitly ensures that we do not leave this region. Finally, I want to draw some connections to regularization methods, such as EWC synaptic intelligence. And these works try to prevent catastrophic forgetting by approximating the losses, as I've said in the beginning. But rather than using old samples, they're going to use second order functions, for instance, in EWC, and based on the approximations of the loss function at the initial minimum of W1. What this does is that the accuracy of the approximation you make of the loss function depends on the distance to your initial minimum. While in rehearsal, you do not have this problem because you use old samples, and because this approximation does have nothing to do with how the initial minimum, there is no dependency on the location in the parameter space. I'm not saying that one of the other is better, it's just an interesting difference between regularization and rehearsal methods, we believe. So this brings me to our conclusion and the two main points I want you to take away from this presentation and our work in general. So we've got our first hypothesis, which said rehearsal works and it's effective because the solution tends to reside in the same low loss region as the task minimum from which it initiated. And we found that this is true. Although the loss increases a bit on, or increases on the first task, we still are inside this low loss region of the first task. And we didn't go to a new low loss region. And the second hypothesis is that we overfit on this rehearsal memory and that this harms generalization. And the conclusion to this question is that this is true, and this overfitting mostly happens at the edge of the low loss region, which is more sensitive to overfitting than the middle of this low loss region. And so I thank you everybody for listening. I hope there's some questions and then we can have a discussion. And I also thank Vincenzo and the people from ContinualAI for this opportunity to present our work here.
Thank you so much, Eli, for your great presentation. I think it was very insightful, and this idea of trying to understand why replay works, since we use that so much, it's very important, and it's actually strange that no one actually worked on that before. So thank you again for these insights, and for the time that you took to explain your work to us. So we have a couple of questions directly put in the chat. Then I see an hand raised, so I'm going to go through that as well. But let's start with the questions that you can see already in the chat. You should be able to read them.
Yeah.
We have a question from Giovanni Zappella. I think it was related to one of the first experiments that you showed. But then I have seen that you somehow clarified with a follow-up slide that you actually consider several memory sizes. Yeah, of 100, 500, and 1000, right?
Yeah. So the different memory sizes is for the step back experiments. For the other experiments, so for these experiments, it's 50 samples per class. Okay. For MNIST, and I think it's 100 for Cypher and medium unit. So it's more than in tiny episodic memories, but less than in GEM and others.
Okay. So you used in the end like a fixed memory for those experiments. And I mean, do you have like a motivation for the let's say choices? I mean, for these memory sizes, or it was like based on just the reasonable size of based on your experience and the related papers?
The sizes itself are just to be somewhere in the ballpark of other papers. One thing we did differently than most is for these experiments, we didn't use dynamic memories. So typically you would say we have a memory budget of 1,000 samples, and first we fill that with the first task, and then later we will cut away samples. We did not do that here because that would not allow us to draw these figures accurately because the memory would change all the time.
Okay, it makes sense. And so we have another question then from Gada. I mean, when you talk about online training, do you mean one example at the time, or do you have like another particular meaning for the online training definition?
No, with online training, I mean that we only allow for one epoch on the data, on training data, and so we use a batch size of 10 samples.
How many? 15
10,
or
10?
10. Okay, so you have like.
So that's 10 new samples and 10 old samples from the rehearsal memory. Yeah.
Perfect. Okay, and okay, then we have Ram. I have seen that you have also posted a new question. So, and I see you have the hand raised. So maybe you can clarify your questions also based on what you have written maybe even before. Feel free to just open your mic and ask all your questions.
Sure. My first question was, could you go to the experiment 2 again?
Yes.
Yeah, I didn't really get what you meant by initialization. Could you repeat that, please, once?
Yeah, sorry. So the initialization, I mean, we first learn the first task. Now we use this model that we found after training the first task as the initialization, which is W1. And then we train on a second task with rehearsal. And the model that we then have is W2. And then we look at the linear path between those two models.
Oh, sorry, I don't think it's this graph. It was a graph like with a dash. It also has the name experiment 2. Yeah, this one.
So that graph is actually, rather than having only one W2 from one W1, we took, you're right that I did not explain that properly. So we took two different memories, and then we trained two models with each their separate memory from the same initialization, from the same W1. And then we looked at the linear path between those two models, which are trained from the same W1, but with different memories. And so we saw then that these two models, even though they're trained with different memories, so different samples in the memory, they are still in the same low loss region, and they did not go to separate parts of this region because the loss between those two models does not increase in between them. Is it clearer now?
Yeah, so one question on this. So let me just like articulate this. let's say your starting point is W1 and you you take a memory, you get W, another memory, you get W2 dash. So what do you mean by a linear mapping between them? What is that mapping?
It's just you take W2 and you take W2 prime, and then you linearly interpolate the parameters of both models. So first you take the models of the parameters of the W2, and then you take a step into the direction of W2 prime in the parameter space of the models, and you calculate loss at that point, and so you continue until you followed like a linear path in the parameter space of those models.
Got it. Thank you so much. So does this mean that, like, is this an experiment to say that it doesn't really depend upon what exemplars you select for replaying? Is that the?
That is one takeaway of this experiment, indeed. But the idea came mostly from that we wanted to see that. So in this, we showed already that we are probably in the same low loss region as W1, but we want to make sure that there's no like weird geometries and that these two models actually end up in a region that is linearly connected. But indeed, the remark that you make is also something you can have from these this experiment, that the choice of the exemplars does not matter very much.
Okay, I have one more question. Like, sorry to take so much of your time, but my question is there any specific reason why you chose this specific setting? So online continual setting. So, and the follow-up on that would be, how would the results of this paper change if you would move to class incremental setting, which also uses rehearsal a lot?
That's a good question, actually. Reason we chose this setting is because that's what I'm most familiar with. But I would not expect the results to change. Actually, I would. Then no, I should verify that, of course, but I don't see any reason why they would change, because right now we do not have like the tasks information while we're training, so moving away from that would only make it easier. So no, yeah, sorry, I don't really have a good answer to the question, but I assume that the conclusions wouldn't change.
Yeah,
that's what sorry.
So for the first two experiments, indeed, it's like mostly in the online setting. But when we look at the step back experiments, we decided to do actually, I think, 10 epochs per task. So that's more like the task incremental setting. And the intuition was like, okay, we really want to like overfit in our memory. So we do a lot of epochs. And in this setup, we also find that it's actually confirms our hypothesis as well. So we show that with our first two experiments, it's mostly in the online setting, but here, when you go to the class incremental setting, it still seems to hold. So.
Okay, thank you so much. My last question is, how do you draw these contour loss plots, if there is a specific technique that we could use as well?
You could certainly use a technique. We have a GitHub linked to the paper, but I could briefly explain. So you just like take these three models, and then you define two perpendicular vectors u and v, and then you just calculate losses for whatever resolution you want, and then you can draw contour plots based on those values.
Got it. Thank you so much.
Yeah, I see Matthias also linked the GitHub repo in the chat. Vincenzo, I think your mic is off.
Oops, yes, thank you. No, I was saying thank you, Matthias, for linking the GitHub. I think there you will find not only the code, but also the link to the archive, the preprint that you can read already. That's great. And thank you, Ram, for your very interesting questions. I think that that pretty much nailed the questions that I also wanted to make. And so do you want, Eli, before closing this session, do you want to just give us like a tagline, something that we can bring home from this paper that you think it's relevant, especially when we want to design new replay approaches, replay strategies? I mean, what do you think it will be like useful for us based on the evidence that you gather in this paper?
I would say use rehearsal, but be careful.
That's nice. That's nice. And so, and also related to this step back idea. I mean, do you think that early stopping would be having like kind of similar effects?
Yes, that is something I gave more thought recently after we submitted the paper, but there is definitely ideas which are in the same sphere as typical regularization on non-continual learning models that would prevent at least a part of the overfitting. Yeah.
Very interesting. So yeah, please, Guy, replay, but not too much.
I have another question if I can ask, if you have time here. If that's okay.
Right.
Yeah.
Could you go to the first plot of your presentation? The first loss plot, the shaded part thing.
Or the drawing.
Yeah.
Like this one or the drawing? This one.
Oh, the initial one. Yeah. So, so this can be aimed towards you or towards the general community of continual AI as well. So, like what we can see, these are just low loss regions, right? So, no matter what kind of example or exemplar you would choose from task T1, there will always be this very less intersection, right? Is that correct?
So there will, like, your question is, will there always be an intersection no matter what?
So I'm not saying there might be chances where there is very less intersection because of like differences, like huge differences between tasks. But if there is an intersection, it might be like a very low region, like a small region of intersection or something.
Yes, although because we can train joint models, there will always be there will always be a part of the parameter space where you have low loss on both tasks. And of course, it also depends on what you define as low loss, because the higher you take the low loss, the bigger the intersection will be, of course.
Yeah, so I'm trying to understand how the intersection region would change. So I understand that if you have more exemplars, it could, like, the intersection region would increase, obviously. Second thing would be if you chose more diverse exemplars, like in the case like iCal chooses, they use herding or something, they kind of want to cover the distribution. So how would that change the region? And like I'm trying to think of the third case in which we can have, we can choose a set of exemplars and then apply heavy augmentations on it and then see how would that affect. So if you have any comments about any of that, that would be really helpful.
Yeah, so yeah, you're like, in the perfect case, we would actually remove this entire shaded area and have the rehearsal memory have the same loss function as the entire test set or the entire distribution. So what we know is that, of course, having larger memories will result in better results. So that would decrease the area of the shaded. There are some works that try to find the optimal selection of samples to be in the memory, and they've got somewhat good results. I forgot the name of that work. So there are people working on finding the best set of exemplars, but it's hard to do. In terms of data augmentation on the memory, I would expect that it works, but I have actually not really seen a work that does do that.
All right, thanks.
Okay, I think Julio, do you want to say just the last question of the session?
Yeah. Thanks for the presentation. I think that's really great. I'm definitely going to read the paper.
Thanks.
My question is, do you think because you can create the memory by GANs and all that, do you think that this same hypothesis can go to those kind of memory or?
You like the generative memories?
Yeah.
Yes, because I think whenever you have like an approximation of the entire data distribution, you will see this effect. And now we've got a mismatch between the true loss function and the loss function from our memory because we have only a small subset of samples. In generative works, this is the same case. The only difference is that you're now generating samples, but these samples will also have a difference with the true loss function from the true data distribution, because unless you have a perfect generative model, which you probably don't. And if you do, please tell me.
No, yeah, my question was because I don't know if these generation functions create the same distribution that the training set, for example. And I don't know if we want to do that because, like you say, we want that this memory can create a representation that not only find a good representation from the training set, but also from all the set of each task, no?
Yes.
So I don't know if you have the experiment for the applying this same hypothesis for the generation memory creation.
No, we didn't run any experiments on generative works because we want to like stay focused on this and like make sure that we have a good explanation for this, or like should be concise, you know. And like my feeling is that the generative works will follow this IDs, but of course maybe we're surprised with what such IDs would give, but
okay, I see. Well, thanks.
Thanks.
All right. Thank you so much, guys, for this very interesting discussion. And I think that Eli, you're also like contributors to Avalanche, the library we are developing within ContinualAI about continual learning. So I hope to see some of these work or in future works integrated into Avalanche as well. That will be useful for all of us. To replicate your results and to maybe expand them as well. So thank you again, everyone, for joining. And for the next reading group session that we're gonna have next week, same time, same day, we are gonna talk about psycholinguistics meets continual learning, measuring catastrophic forgetting in visual question answering. With Claudio Greco, so please consider also joining next week, and I'll see you then. Bye.
Bye. Thanks.
Bye. Thanks for hosting.
Thank you.